It's 10 past. Time to get started. Thank you very much for all showing up here. I wanted to talk a little bit about deep learning pipelines. This interest started about a year and a half ago when I saw there were a lot of tutorials explaining me how to build a certain model, which models are best for which kind of problem. But what I saw when talking to users or to people who do that in production use cases, the biggest challenge for them often was like, how do they do all this stuff around? So not the learning aspect, but how do they get the data into the system? How do they store the models? How do they serve the models? And I've been pleasantly surprised by this year's TensorFlow Dev Summit. Has anyone attended that virtually or in person or watched the videos? I can only recommend to do that. They actually put all the videos online from that event. And it's actually, even if you don't use TensorFlow, it has a lot of good stuff of what it means to run machine learning, deep learning workloads in production use cases, because about 50% of the talks were actually focused on this aspect, like besides learning, onto serving, onto data ingestion. So that was quite interesting to see, and there were also a lot of good discussions around that. I'm hoping that the slide will go forward if we reconnect to the internet. All right, let's improvise until the internet is back. All right, I'm Jörg. I'm a technical lead for community projects. That means in the at Mesosphere, I'll tell a little bit about that, just one or two sentences later on. I'm responsible for projects which are not on the official roadmap. So I, for example, work with TensorFlow. I work with Flink to make sure that they all run well on MESOS and DCOS. Let's hope that internet is back and connected. Yes. So deep learning, what is the promise? We've probably seen many of those slides already today, but for me, kind of this main promise is that I'm taking this human expert out of the picture who used to sit there in traditional machine learning and kind of compile the features for me. So that was kind of like an expert in some domain, and he would apply this expert knowledge onto the feature extraction. Then we throw in like some compute power, and we get some model out of that to, in this example, classify is this a dog or not. With deep learning, we actually replace this human by a lot more machine power. So that has multiple advantages. First of all, we don't have to have this expert anymore. I mean, we still need some experts around building all this, but we don't need this domain expert extracting the features anymore. And we actually also less biased. So as we're doing that in a purely data-driven way, deep learning, we actually can find the different features which might represent or solve our problem better, model our problem better than this human could do that. So that is a promise. The process, very simple. So we have like a large data set of labeled dog pictures. Then we go through, we build our neural network, we train our neural network, and then hopefully we have a trained model with some weights who can tell us, is this a dog or is this a panda with a certain probability. It would be great if that's as easy. So let's actually look at how a network can do that, or what is kind of our intuition of how it should do it. So usually, like a network is built in multiple layers here, and typically the first layers, they pick up very simple features, as for example a line, as for example a circle. And then the layers further down in my model, they actually can construct more complex features, more complex objects out of those simple features. So it kind of continues building up on the previous layers and building up a more complex identification model. So here we first identify lines, circles, then we can actually identify in the next layer, is this a nose, is this an eye, is this fur? And then at the end we actually can assemble that, is this a dog or not? So this is kind of the idea of how this should work. So what are the challenges? How many of you have used TensorFlow before? I really like TensorFlow, especially it's so easy to just spin up a Docker image or even run it just pure on my machine and just train my first model. There are also a lot of great tutorials of how to start. So just being the single developer sitting there at my own machine, TensorFlow is really great. But it becomes more challenging if we look at how this is applied in like a production use case, because there we actually have a whole pipeline. So we somewhere have to store our input data. We have not just TensorFlow. There are actually many other frameworks which are all being used in production use cases. So we kind of have to deal with this universe of different frameworks here. Then not all users are actually domain experts and want to write some Python code to deal with their machine learning models. So we might have to have a different interface for our users. So some notebooks such as Jupyter or Zeppelin notebooks. And then we also have to be able to train and serve those models. So we have to take care typically of a large cluster with GPUs. If we're running in the cloud on Google, maybe even TPUs. So we kind of have to take care of this entire cluster. And as we'll see, typically, often it's not just the TensorFlow cluster. It's actually we're having a Spark cluster as well. We're having some Kafka streaming our input data. We might have HDFS for storing our input data. So we have a kind of complex cluster to manage. After we have trained something, we actually end up with a large number of models. So if we just flip back to this initial picture here, what's kind of misleading, this isn't one trained model. Those are like hundreds to thousands of trained models, because we do it for different hyperparameters. We might get more input data and retrain our model. So there's actually not just one trained model, but a lot of those. All right, so we kind of have to deal with all those models in some way or the other. And then we also have to serve those models. So model serving means we have to apply them to like some real workload. So in our doc case, this could be like some camera images coming in, and then we have to decide in close to real time, is this a doc or not? So we have to utilize this model to infer some knowledge using this model. And what we shouldn't forget, there's like monitoring and operations across this entire platform. So we have to monitor for our performance of our different models we've trained. We have to keep track of the entire infrastructure. So just for failures, is an AWS node down? Is a Google Cloud instance down? Is somewhere the network down? So the traditional distributed systems monitoring. And then we also have to do operations such as debugging, monitoring, exporting, storing data, so upgrading the framework. So there's a lot which actually we have to do across this entire picture. And we'll look at each of those in some more detail. So training challenges. As mentioned earlier, we don't just train one single model. We train a bunch of those. So this is actually a loop. So we have a trained model, we go back, and then we train the next model. And this, first of all, each of those iterations involves hopefully a lot of data. The more training data we have, typically the better. And then we also are iterating over different hyperparameters. So for example, the different number of layers, the different number of units in each layer, and then, for example, also the learning rate. So we are changing some parameters and try to figure out which of those set of parameters gives me the best model. And there's actually a lot of research right now and a lot of interesting papers and techniques of how to explore this space of hyperparameters. So whether I just go in there and change some values randomly, or whether I can do a more informed search across this space of hyperparameters, because not all of us have the compute power which Google has and can spin up like 200,000 TPU hours to train their model. Most of us have to be a little more conservative and cost effective. So it's really worth looking at those different techniques for optimizing the hyperparameter search. Input data management. So first of all, we have hopefully lots of data. So we have our training set, we have our dev set, and then we have our final validation test set. Plus there might even be new data coming in. And for me, typically the biggest challenge in machine learning is how do I pre-process that data? Typically, the raw data we have isn't good to simply throw it into a TensorFlow. So what I see many people spending at least as much time on as building their the model is the pre-processing of the data. Cleaning up images, figuring out which images are, for example, mislabeled. So someone might have labeled this image cat or sun or something, which might be partially correct, but in this case, this box should actually be labeled dog. Then this data should be available on our cluster. And this, especially if I'm going into those cloud settings, can become an issue because, as mentioned, those are large amounts of data, and I might not even be allowed to upload this in a cloud due to this being sensitive data, which I have to keep in my own data center. The other case is, this is mostly for inference later on, so where I have to decide whether this is a dog or not, is that I might actually have a stream of data coming in. It might not be a set of files, but it might be a set of messages coming from a Kafka queue with those different images, and then I have to infer on those pictures whether dog or cat or whatever. And so what we typically see is a mixture of different ways to store this data. So HDFS or some kind of distributed file system, if we are also in the cloud, very helpful for just storing this massive amount of data. Then sometimes if I have structured data, I want to use something like Cassandra, so a distributed database. I always feel a bit bad saying database to Cassandra, but different topic. And we also might have a stream of data coming in, such as, for example, with Apache Kafka. All right, frameworks. So what is TensorFlow? So TensorFlow is just this library for machine intelligence. It's way more than just deep learning, but typically people nowadays use it for exactly coming up with those deep learning neural networks. And the nice thing about TensorFlow and most of those other frameworks is that they give me some kind of API. So I can write Python code, and if I do that correctly, TensorFlow can actually compile that to different backends. We'll talk a little bit about what the pitfalls there are later on. But if I'm doing everything correct, TensorFlow can generate GPU code, CPU code, and also nowadays TPU code, so this new tensor processing units which Google is offering in their cloud. There are different alternatives, and all of those alternatives have different advantages and disadvantages. So the typical distinction, for example, if I'm looking at PyTorch, which is why I liked PyTorch for a long time, for many scenarios better than TensorFlow, was the way they're dealing with the graph. So if we look at a typical TensorFlow program, we're first specifying our entire graph. How should the graph look like? And then down here, we have session init, and then we are actually running this graph. So we first construct the static graph and then run it. This is not great for all problems. So if for example, also for debugging, this is rather bad because I have to debug the entire graph at once, which can be really annoying. So other frameworks such as PyTorch, they early on adopted a more dynamic approach. So here you see you're actually constructing this graph while you're running it. So at each of those steps, you can actually just throw in a print statement or even abort, build a different kind of graph. So this is kind of a more dynamic execution graph for my model. Luckily, TensorFlow also has adapted to that. So there's this enable eager execution, which allows me to do pretty much the same thing. So build a compute graph on the fly with TensorFlow as well. It's not as well tested, but it works rather well, I must say. Having that said, you should keep in mind that both of those approaches have advantages and disadvantages. So this dynamic approach is great if I need something dynamic. So if I'm doing speech recognition or translation where I might need to abort if there's a full stop, if a sentence ends, then a more dynamic thing can be great. On the other hand, if I'm having the static graph, I can actually, or TensorFlow, I don't have to do that, can do a lot of optimizations because it just has the entire picture, the entire knowledge, and especially in recent versions, there's a lot of operator merging. So there's called XLA, which is kind of the library behind it, where they actually allow to kind of merge operators. So those of you who might have worked with Spark and know about the Tungsten project in Spark, this is kind of a similar project for TensorFlow where they can merge stuff. And this is, of course, way more effective if I know the entire graph as when I'm stepping through here. So what we are often seeing is that people are just stepping through when they're developing a model, and once they fully understood it and fully have developed it, they sometimes just switch over to the static graph, as in many cases it gives me better performance. We've seen two examples. There are way more. A lot of people use Spark, MXNet, XBoost, and so there's actually a lot of choice in this ecosystem here. And even inside TensorFlow, I've seen that actually people starting to write code about 2-3 years ago, so with the early TensorFlow version, so even like a year ago. And early on in those days, it was really hard to write a distributed code. And a lot of those people are now coming to us, for example, or to other people, and they're like, can you help us actually make this TensorFlow program run distributed? As of today, there are really cool libraries in or APIs inside TensorFlow. So especially if you can try to use those estimators. So those estimators make it really easy to specify an estimator of what you want to do. And by the library, TensorFlow is then able to execute that in a distributed setup, even using TPUs very easily, and you don't have to manually specify, for example, where you want which task to run. Besides that, there are also a lot of canned estimators. So kind of for the standard use cases, like DNN or inception use cases, convolution, there are pre-built estimators which you can simply use from the library. And I think Google has done an internal study that at least 50% of the TensorFlow code is using those canned pre-built estimators. So this should give us like an indicator where that they're actually not that bad. The other mid-level API, which I like a lot, is the dataset API, because they give me a more abstract way of actually dealing with data inflow and how to deal with my data sets. All right, this was about frameworks. Now let's talk about the users. So I often have users such as data analysts, which don't really want to deal with any of those APIs here we saw earlier. They simply want to explore the data. And for them, projects such as Jupyter notebooks, such as Zeppelin notebooks, they're really cool because they can come up with an interactive environment where they can then run build their TensorFlow program, their Spark program, and so on, or model. And so those notebooks actually give a very easy and intuitive way for data analysts to interact also with the cluster, with this compute cluster. Those people typically don't want to think about, is there like a large cluster behind it? They simply want this to work. One project which has been open sourced just a few weeks, 1.5 months back, is called BeakerX by 2Sigma, and this gives me a lot of extensions for Jupyter notebooks. There used to be a version about 1.5 years ago of BeakerX where they tried to build like their own notebooks from scratch. But with this new version, they're actually just extending Jupyter notebooks. And that gives me a lot of stuff, for example, JMX metrics, and a lot of other cool features if I'm working with Jupyter notebooks. Other people, mostly in the Spark area, they're more on the Zeppelin side, so it gives me similar experience, more. So I typically see people using TensorFlow, they're on the Jupyter side. People using Spark prefer Zeppelin. Okay, this brings us to the cluster, and as I'm working on MESOS, this is kind of the topic which is very dear to me. So the typical workflow, if we do it with TensorFlow or with any other library, on a single machine, as mentioned, it's very easy. I download the library, I spin it up on my machine, I write my code, it gets optimized for whatever number of CPUs I might have specified there, and then I can train on my single machine. Unfortunately, if we look at how it works for a distributed setup, it becomes more complex. I have to set up different workers. Each of those workers might have different capabilities. It might have GPUs available. In Google Cloud, it might even have TPUs available. I have to set up some parameter servers. So it becomes a distributed architecture and setup. And as we are distributed, there also failures can occur at any time. If I'm dealing with such kind of system, I also have to look at how can I do resource isolation or resource allocation. So again, if I'm having one node in my cluster which has GPUs available, I kind of have to make sure that only one task at a time will use this GPU, and I have to make sure which task that should be. So I need some kind of system which is allocating those resources to different TensorFlow frameworks running, to different TensorFlow clusters, and also ensures that no one else can actually interfere here. TPUs, it's the same story. Said they are kind of the Google specific version. So they build units which are specifically only implementing the operations you need for this deep learning. So matrix multiply plus some vector typically. And they're really efficient at that. And if you run something in Google Cloud, you often even can get like an entire rack of those, which is very, very powerful. Just imagine like 11.5 petaflops, what that used to be like 5 years ago. Okay, what does that mean for your data center? As we mentioned, there are multiple frameworks running. I might have several TensorFlow versions running. I might have a TensorFlow test setup, dev setup. I might even have then a Jenkins, Kafka queue, and some people might even use Spark. So the old approach, which we still see a lot of people doing, is to kind of take the first 5 machines for Spark, the next 10 machines for TensorFlow, and so on and so on. You get the idea. I must say this works well if I'm in a cloud environment where I just bring up instances. Or it might work there well because I have a well-defined interface. But latest, if I'm on my own cluster, this becomes an operational nightmare because my administrator, my operator actually has to take care of that. If a node fails, he has to go in and restart that. And this used to be the core idea of Apache MESOS. Back when Twitter was having those fail whale problems. It used to be a research project at UC Berkeley, same lab which came up with Spark, by the way. And so the view is to just see it as a big resource pool. Similar as my laptop here, it has multiple CPUs. I don't care which one is currently being used to present that. I simply want that one CPU is being used for that, or part of one CPU. And this is kind of the vision MESOS has for the data center. View it as a big resource pool. In such kind of cluster, you of course also have other problems. What are failures? There might be network failures, node failures, task failures. So I hope in my laptop all my CPUs are going to stay stable. But in a cluster, I can't really expect all my nodes to be up all the time. DCOS, just real quick, is kind of a distribution built around giving me all frameworks. So in the end, it gives me the flexibility of running all different kinds of workloads, TensorFlow, Kubernetes, Spark, and so on the same shared cluster. And also to the down, it gives me the flexibility to run on any infrastructure, whether that's on cloud, on-prem, hybrid, a mixture of both of those. Okay, and with that, you've seen like those things up there. So they're actually pre-packaged versions. So I only have to say DCOS package install TensorFlow. It's also all open source. And it spins up a TensorFlow cluster for me. And we'll hopefully see that in a second. As mentioned, if I'm having my first TensorFlow cluster, or actually any distributed system, so Spark, Cassandra is being spun up, dealing with failures is hard. So in terms of TensorFlow, if I have too many failures, it might actually mean I have to stop training, change my cluster spec, and then restart my job. And if we look at this role of the administrator or operator we've been talking about before, he also has to manage all those different frameworks and all those different failure cases. And especially at 3 a.m. at night, being woken up because HDFS node failed can be really annoying. So this is the second idea of MESOS, is to kind of have this two-level scheduling. So the first level of scheduling is the resource level, where Apache MESOS is saying that many resources should go to Flink, that many resources should go to Spark. But then for each of those frameworks, we actually have so-called scheduler. You can also imagine it as being an operator. And this operator, for example, knows what happens if an HDFS name node is failing. It knows how to deal with if 2 HDFS name nodes are failing, because then it has to recover from the journal nodes. So it kind of encodes this operational knowledge and relieves me as the real administrator operator to be woken up at 3 a.m. at night and having to fix that. Okay, so what happens if I'm running TensorFlow on MESOS? It restarts a failed task, and my cluster can actually continue to being picked up by this checkpoint, and then can continue running. All right, next, model management. Recall, we are dealing with a lot of those models, so we're not training one, we're training hundreds to thousands of different models here. So we kind of have to take care of where we store them, how we treat them. And so typically they're kind of like these two things. Some people store that together, other people actually store that in separate entities. So first of all, it's the model itself, which has to be stored. And they're like distributed file system typically is good, HDFS, GFS. And then the metadata also has to be stored. So what was the inference performance? What was the training performance of this particular model? And there I've seen people either store that in some kind of structured data store, such as MongoDB. I personally built a prototype using ArangoDB because I like ArangoDB. It's a mixture of a document store and a graph store, so I can both model. Each model has a document describing all the performance characteristics, but then I can also have connections between different models. So for example, I can say, this is a refinement of this model. And I can kind of capture that very easily in as metadata. Does anyone know TensorFlow Hub? Cool. So with those models, as said, if Google is training a model like Inception, they're spending probably somewhere like $500,000. Those are typically like 100 to 200,000 hours of TPU learning time. And this, we as normal developers, we never can afford that. So there's actually this project called TensorFlow Hub, where people upload pre-trained images, models. So for example, I can simply pull down a ResNet, Inception. I'd strip off the last layers and train it specific to my smaller data set. But first of all, I don't need this huge data set which has been initially used to train Inception, the Inception network. And secondly, I also don't have to spend that much time training it. Previously, those models were flowing around everywhere, and I really like this approach of TensorFlow Hub, so similar as Docker Hub, as GitHub, to provide like a common store for those where also anyone can contribute new models to. Model serving. So model serving, it's how should I deploy those models into production? Often, if I'm having an online scenario where I keep on serving user workloads, I even have to do that in like a zero downtime meaning. That means I have to keep serving models while I'm updating or bringing in the next one. I might even have canary deployments that I want to test a new model on live workload. How does it behave? How long does it take? Maybe it has better accuracy, but way slower performance. So I'd never really want to use it in my production use case. And the way TensorFlow Serving is dealing with this, so it has like a source folder you can configure, and there it's watching for new models to be stored. Those models are being loaded into the dynamic manager. Then here we have a version policy which decides then which model should be used in production. So if I'm uploading a new model, the version policy could, for example, check this metadata store we've been talking about here. What is the accuracy? What is the inference time? How long does it take? Should I use this model or not? TensorFlow Lite, another raise of hands. Who has seen that? Cool. So TensorFlow Lite, I put it in here because I find it very interesting in which direction it's going right now. So those trained models, they can be rather large. Sometimes I've had some with like 50, even up to like 80 megabytes. And first of all, this is a size thing. I never would want to put this here on this device. And secondly, it also impacts, of course, the speed at which this fully trained model would evaluate a new picture coming in. So there's actually this new project called TensorFlow Lite, and they take a trained TensorFlow model, they have this converter, and they actually bring it down to somewhere between 300, maybe up to 1 megabyte, but at least like much, much smaller. And they do that with certain optimizations. You can also configure how accurate you want it to be, or whether you allow this transformer to actually change the model structure also a bit, dropping gradients and so on. Changing model weights, that it might become smaller. So this is something which I find very valuable because, first of all, it's smaller. It runs in different environments. If I want to run on a Raspberry or some other kind of integrated system, I typically don't want to have those large models. And secondly, it's also just typically it's much faster. On the other hand, this isn't the same model which comes out here. So this is actually a different model. So I should retest that whether it still fits the accuracy requirements I might have. Rendezvous Architecture. So this is being proposed by Ted Dunning from Mapper. And it's an interesting way of thinking about how we could deploy those different models. So what the Rendezvous model assumes is that I'm serving multiple models at the same time. So here I'm getting my request. Again, let's take this image with dog or not, and I actually feed it at the same time to different models. And then once they are done, they actually push their result onto a scoring function. And then the scoring function can actually decide which of the results should be used and returned to the user. So this allows me to kind of have canary deployments for new models, see whether they match the same performance, or even implement something like a majority vote. If two models say this is a dog, one is saying this is not a dog, I can take a majority decision here. Oh, by the way, I have a lot of links, both on the slides and also in the notes, so feel free to check that up later on. Last part is about monitoring and operations. So first of all, we have to understand what's going on. And there, TensorBoard, there are other similar projects for example, PyTorch. But I feel TensorBoard seems to also become the standard, so other projects are trying to integrate with that. And so for example, while this model is training, what I want to see in TensorBoard is like, how is the performance developing over time? Because that might also be an indicator that I can actually stop training because it's good enough, or that it's still fluctuating a lot, which means I might have to adapt my model. And we also have to monitor, as said, the overall cluster. So they are typically traditional cluster monitoring tools such as Datadog plus metrics are a good solution. Next thing is debugging. Who of you has used TF-debug? You've done everything. So TF-debug used to be this very nice console. I guess all of us, we want to use that. So maybe why do we want to use that? Especially those static graphs, they are kind of hard to debug, and their TF-debug is really a great improvement, but it's just not nice working with that. So they actually now have an alpha version of the new GUI available. I said it's alpha, it integrates with TensorBoard, but here you can already see it gives me like a much nicer, easier to understand picture of the overall graph structure as well. So I think this is a huge improvement for being able to debug my models also during training. Did I want to say anything else to debugging? No, we'll come back if it was important. The other really important thing everyone should consider and also practice, because it takes a lot of practice. So those different models, they take a lot of performance optimizations. And those performance optimizations, they're typically based on some experience, like that 8, for example, is a magic number with GPUs, and I should have block sizes multiple of 8. And other things, plus profiling. So this performance guide is on the TensorFlow side. This is actually pretty good. It gives you concrete advice what to do if you're running on CPUs, on GPUs. So that's a great starting point to start out when trying to improve your performance. And then a profiler like the TensorFlow profiler, they give you this graph here, and this took me probably 1 or 2 days to really be able to utilize that. But once you have done that, it's very, very powerful. So the normal pattern in profiling or performance optimizations with those models is that you want to keep your devices busy. So especially if you're having GPUs or TPUs, you're trying to optimize your code that those are working and processing data all the time. So this is typically the first thing I would look at here is how busy are my GPUs, how effectively am I piping data over to them. Platforms. So we've been talking a lot about those different steps inside machine learning, deep learning. There are actually platforms which kind of give that to me. So there's, for example, SageMaker from AWS. And all of those platforms, they kind of follow the same pattern, or most of them. They typically give you some kind of notebook, most of them Jupyter notebooks. As mentioned, this is a great way to interact with it being a data scientist. Then they have some training jobs where with almost all of them, I can actually choose between different kinds of jobs. So for example, SageMaker has Spark, MXNet, TensorFlow. Then they have, being a cloud platform, SageMaker has some way of storing those models, and then also an endpoint for serving those models. And this is where they kind of differ a bit, as like how much do they offer, especially back here, and in terms of different jobs. So for example, SageMaker, they make it really easy to run A and B testing. So similar as with the Rendezvous architecture, I can actually test multiple models at the same time and see what their performance is. What I also like about SageMaker is that I can actually specify my own Docker images. So I find that very powerful when I want to tweak something, I want to do it this way, whereas with Google ML Engine Data Lab, I'm kind of restricted to their control. It might not be an issue for you, it's just I found it very nice as it gave me a lot of flexibility. Then there is Kubeflow, which kind of implements this basic flow we're seeing here. So Jupyter Notebook, TensorFlow serving on top of Kubernetes. But that's TensorFlow only, and it's kind of opinionated a bit how they deploy that. But it's a great start if you don't want to start in one of those cloud environments. So for me, the biggest disadvantage of the first two, they give a really easy experience, but I'm kind of then tied to those cloud providers, and they make it really hard to switch. So for example, they also differ in the choices of GPUs they support, and of course Google is the only one supporting TPUs, so they really try to kind of make me stick to them, and once my workload is growing, this might become really expensive. So often we see people which want to move an on-prem setting, or they might even have to do it due to data privacy issues. And then last on this list is DCOS. So this is what I showed you a bit earlier, what I'm working on. What's nice about DCOS, it gives me all this flexibility of installing actually anything I want and build all kinds of pipelines, even install HDFS on the same platform, Cassandra on the same platform. It has really good GPU support, which has been running for years now, also in production. So very good GPU isolation, but it involves some more manual setup as compared to the other ones. So depends on how dirty you want your hands to get setting this up. One other platform project which I personally like a lot is called Pipeline AI, and they built a lot about the inference and serving layer, A/B testing, and give you a lot of metrics of those. So they also have an open source community version. As I got assigned 1 minute, I unfortunately won't be able to show you the demo, which would have been like a walkthrough of pretty much this. But I think that's okay. I have more links in here, and as said, on all slides are also links. Last thing I want to say is special thanks to especially Sam and Kevin. They implemented a lot of the GPU support in MESOS and also the TensorFlow on DCOS. So I can simply install my cluster with DCOS package, install TensorFlow. All right, that was the talk. I might just flip over to the cluster and just hit install TensorFlow to just show you some part of the demo. But in the meantime, I'm also happy to take questions. So review and run. And this job will fail as I'm specifying an invalid job URL. So the job URL is kind of where is my data stored. Test, review and run. But what this will do right now, it will spin up a TensorFlow cluster for me, depending on how I configured it. So here, for example, I can set the number of GPU workers, the number of workers, whether I want to use TensorBoard, how many parameter servers I want, and then this will spin up this cluster dynamically for me. Okay, any other questions? All right, otherwise I'm around. Thank you very much for listening.